Okay, so we've talked about heat is really an amount of energy that gets transferred between substances that are at two different temperatures. So the next question we want to ask is, okay, so what happens when that energy is transferred as heat? And basically we're going to focus on two options. One is that the temperature of the substance will increase, or two is that the substance is going to melt or evaporate. Well, what if you, instead of transferring energy to a substance, right, adding energy, what if you subtract energy? So when you transfer energy from a substance. So again, you got two options here. One is basically the temperature is going to decrease, or the substance is going to freeze or condense. So things that start as liquids will freeze into solids. Things that start as gases will condense into liquids. So basically what you can see is that there's two types of processes that occur when energy is exchanged as heat. One is there's an energy transfer with a temperature change. That's the first one, right? The temperature increases or the temperature decreases depending on whether you're adding or subtracting energy. And the second one is you have an energy transfer with a phase change. So when you get to the right temperature, and so if you have something like ice and you get it to the right temperature, and the right temperature just means the melting point, as you continue to add energy, it's not going to change temperature, it's going to change phase, so that ice will begin to melt into water. So these are the two processes that we're going to deal with. So how do we keep track of the energy transferred as heat if the temperature results in if the temperature of a substance changes? So that energy transfer results in a temperature change. And the broadest definition is that we can talk about the heat capacity. And the heat capacity is basically just a way of saying that the energy transferred in as heat is proportional to the temperature change. And so the heat capacity is a measure of the amount of energy required to raise the temperature of a substance by 1 degree. So basically it's the proportionality constant that says you have to add in this much energy to get a 1 degree temperature change for your substance. The heat capacity, big C, depends on two things. So A, what the substance is. Are you talking about water or ice or some metal or some gas, or so what the substance is. And then two is how much of the substance there is. And so what we often do is break that apart into two pieces and talk about the specific heat, little c. So the heat capacity gets capital C, the specific heat gets little c. And so notice that basically what we've done is we've taken those same two things, the amount of stuff and the type of stuff, and just split it apart into two things. So the specific heat is a measure of the amount of energy required to raise the temperature of 1 unit mass, because we've split that piece out, of a substance by 1 degree. So it's basically the heat capacity per mass. So a specific heat process requires a temperature change. So you're going to see a temperature change as this energy is transferred into or out of your system as heat. The specific heat value itself is a property of the substance. So if I tell you what the substance is that's exchanging energy, then you know what value to go look up. So if I tell you that, hey, it's lead, or it's a gas, or it's water, then fine, we need to go look up that particular specific heat value that's unique to that substance. And then the last thing is that the sign of a specific heat process is determined by delta T. So delta T, T final minus T initial, is positive if the temperature increases, and it's negative if the temperature decreases. So what this means is, if the temperature increases, Q has to also be positive, because we know mass is positive and the specific heat is also just a positive number. So temperature increases mean that your substance has to take in energy as heat. Temperature decreases, this will be negative, these two will be positive, which means Q will be negative. So again, temperature decreases only occur when your system gives up the energy as heat. Units. Well, the units of specific heat, since we want to end up with an energy that's in joules, and then we're basically multiplying the specific heat by a mass, so per kilogram, times a temperature per degree Celsius, so the SI units of specific heat are just joules per kilogram degrees Celsius. So that's dealing with specific heat processes where there is a temperature change. With a latent heat process, there isn't a change in temperature, but as you keep adding or subtracting energy, there is now a substance change. And so our latent heat processes, we have two types, but they all have the same form. So there's a latent heat value that's capital L, and so the energy transferred into or out of your system is going to be given by the plus or minus tells you whether you're transferring energy in or out, the mass, and then times the latent heat value. There's two types of latent heat. There's the latent heat of fusion and the latent heat of vaporization. The latent heat of fusion is when you have changes of state between solids and liquids. So either you have a solid that's melting or a liquid that's freezing. Latent heat of vaporization is when you have phase changes between liquid and gas. So you have a liquid that's starting to boil, converting into a gas. You have a gas that's condensing, converting into a liquid. So the latent heat process requires a phase change, right? Temperature isn't changing, but you're at these particular special temperatures where now the phase will change. It is a property of the substance, so different materials have different latent heat values. So again, we just go look those up. And then we are now responsible for the sign of a latent heat process. So if we're adding in energy as heat, that means that we're taking a solid and melting it, or taking a liquid and boiling it, and those will be positive. If we're losing energy, taking energy out as heat, energy is being transferred away as heat, then we're taking a liquid and freezing it, or we're taking a gas and condensing. But we're responsible for the sign. There's nothing else in here. Both of these are positive values. There's nothing else in here that's going to take care of that sign for us. The units of latent heat, well, again, I want to end up with an energy, and all I'm doing here is multiplying by a mass. So latent heat values have to have units of joules per kilogram. These values are often large enough that when we see them reported, we'll see them reported in kilojoules per kilogram. So just be aware of that. All right. So when you have something, you have some substance, and let's say you start with some solid substance at some initial temperature. As you add in energy, what's going to happen is you transfer energy to that substance as heat. There's going to be a temperature increase until it gets to this particular temperature, the melting temperature. As you continue to add in energy to your substance, well, now it's not going to change temperature, it's going to change phase. So because you're at the melting temperature, that additional energy goes to breaking up the bonds of your solid and turn it into a liquid. Once it's all melted, now as you continue to add in energy, again, it's going to increase in temperature. So this is basically a temperature over here versus the energy you're transferring in. And you can see that there is if we start as a solid at some initial temperature, we're going to increase the temperature to the melting point, then we're going to melt the substance, then we're going to increase the temperature to the boiling point. Again, we've reached a special temperature here where for this substance, as you continue to add energy, it's not going to change temperature, it's going to change phase. So now you're going to have, as you add in that energy, your substance is going to boil. And then again, once it's all boiled away, so now it's gone from liquid to gas, as you continue to add in energy, it will increase in temperature again, up to some final temperature. So notice as we go from some solid below the melting point to some gas above the boiling point, there's actually 5 processes involved in doing this. 3 of them are specific heat processes because, again, there's very clearly a temperature change here from the initial temperature to the melting point, from the melting point to the boiling point, from the boiling point to the final temperature. So clearly a temperature change, so these 3 are specific heat processes. There are 2 latent heat processes. So again, here we're not changing temperature. Here we have a latent heat of fusion because we're melting. So we're at the melting temperature, but that energy is going to change the phase. It goes from solid here to liquid there. Here we have a second latent heat process where it starts as a liquid, we continue to add in energy, and it ends up as a gas. So the temperature, it's at the boiling temperature, at the boiling point, but that's going to, as you add in that energy, it's going to change the phase here from liquid to gas. So these are the processes that we're going to deal with. And again, for most of y'all, you'll be familiar with these because you've seen them in chemistry And just like in chemistry, we're going to build them into working with calorimetry problems. So that's what we'll focus on in class tomorrow.